Okay, let's proceed. In the last class, we looked at the idea of reciprocity and inter-reciprocity. So we saw that if you have a linear network consisting only of R, L and C, you can apply an excitation here and measure the response at the other port, and the same response can be obtained by applying the excitation on the second port and measuring the response at the first port. And you know the combinations of excitations and measurement quantities. So for example, if I apply a voltage V1, here I will measure a voltage V2. So what do I apply here? We apply a current, say that is I2 hat, and measure a current I1 hat, right? And we saw that the ratio in the frequency domain is equal to I1 hat of j omega by I2 hat of j omega. And in time domain, what does it translate to? Yeah, so V2 of t convolved with I2 hat of t is V1 of t convolved with I1 hat of t, right? And of course, we know for the other combinations of input and output, what is the corresponding excitation we have to apply. So if you stare at this, this says that the transfer function from the input voltage V1 to the output V2 is same as the transfer function from the current I2 hat to the current I1 hat. So if that is the case, what can you say about the impulse response? I mean, I'm saying the transfer function from here to here is same as the transfer function from here to here. Then even the corresponding impulse response will be equal. So how do I get the impulse response here? Okay, copy paste once. So my input is a voltage that is applied here, and output is a voltage measured here. To find impulse response, what do I do? I'll apply an impulse voltage here, okay, and I'll measure the voltage V2, and that should give me the impulse response. Similarly here, we'll apply a impulse current. So this is delta of t, and I'll measure what is I1 hat of t, and seems like these two are equal, right? So are these two equal? I mean, at least sanity check. This is a voltage, this is a current, right? So obviously you can't equate an apple to an orange, right? So what's the deal? What's the missing thing here? I mean, at least till here it's fine. Here quantities are dimensionless, right? We saw that the transfer function from the voltage V1 to the output voltage V2 is same as the transfer function from the current I2 hat to the measured current I1 hat. This much is clear, and this means that obviously the impulse responses are also equal, right? This I call it as some transfer function, say h. Yes, so this is basically these two are equal, and as he points out, that is one thing. See, if you think about it, if you use a time domain relation, right? Here I have V2 convolved with I2 hat. So what is I2 hat? Delta of t, right? So basically we have V2 of t convolved with delta of t. Okay, this is a current, remember. So what is the dimension of this quantity or units of this quantity?
Voltage, complete voltage is
No, this is, I mean, this is a current, right? I mean, Yeah, let me write it directly, right? I don't know. It's not. Let me copy this. Yeah, oops. Yeah, this is basically gives measure of energy. I mean, this is volt, this is ampere. When you convolve, you have a second comes in. So here dimensionally things are correct. Okay. And other fine point to note is the moment I say that I am trying to measure impulse response. So here you are saying that my impulse response h of t is v2 hat of t. Is that the claim? I mean, I want to find the impulse response. Everyone unanimously told that I need to apply an impulse voltage here. And since my output quantity is a voltage, I'll measure the voltage. And so how do I find the impulse response? I mean, what is impulse response?
To the output to the impulse input.
Output response in response to an impulse input. This is the output response in response to an impulse input. So, are these two equal? Okay, let's do no convolution here. I mean, just plain, right? There is no. Let's say you don't know anything about impulse. I mean, convolution. Impulse response by definition is the response of the system when you apply an impulse. Okay. So, what is the units of this? V2 of t. What is the unit of impulse response? Huh? You don't get that.
Volt second.
Huh? Volt second. What other units? Okay. What did you say? 1 by second, huh? Okay. That's hertz. This is option A, option B.
So we are giving an input as the voltage. And
Yeah, yeah.
output is also the voltage. So
Correct.
This h of t should be unitless.
So, okay. Option C is
1 by second.
1 by second. Here also going 1 by second. Okay. So, how will you find? Yeah, I mean, the whole point of having the impulse response, I mean, what does impulse response help you find?
Impulse response is just fine. Response to any
Any arbitrary input, right? So, input is say v1 of t, my output will be integral h of t minus tau. This is fine. So, I know this has units of volt, v2, v1 has units of volt, this has units of second. So, what should be? This should be hertz. Okay. So, basically, the impulse response has units of hertz. So, what this means is that if I apply an impulse and say I measure the output voltage to be something like this, say going from 0 to 0.1 volt, the impulse response has the identical shape going from 0 to 0.1 hertz. So, okay. So, to be really correct, I should multiply this with what? I mean, here I have volt. I need to get
1 by volt.
1 by volt second, right? Okay. So, impulse response is the voltage times 1 by volt seconds. If your input is voltage and output is voltage. Fine? Again, similarly here, when we say we are measuring the impulse response, so even here when I measure the impulse response, when I apply an input current and measure the output current, so from I1 hat of t, what should I do to get impulse response? 1 by ampere second. Is that fine? And what is an ampere second? Yeah, it's basically 1 coulomb. Okay. So basically 1 coulomb.
flux here.
Sorry? Yeah, we can see that, yeah. So, okay, fine. So, from this, let's look at this. So, where is this 1 coulomb coming from?
Input current impulse.
Yeah, basically when I say an impulse current delta of t, this is 1 times delta of t, right? What does this 1 signify?
Coulomb of charge.
Yeah, it is the area of the impulse, and here we are talking about a current. So the area of current with time is basically charge. So when I say delta of t, it just means I am putting in a 1 coulomb of charge instantaneously into the network. Okay, cool. So yeah, this is a fine point to note. So if you were to find the impulse response when you are applying a current and measuring a current, you measure the current, and dimensionally to be consistent, you will have to multiply by 1 coulomb. Okay, cool. So yeah, this is with respect to RLC. Now we saw that if the network also has control sources, the reciprocity assets will not be valid. So what do we have to do? Yeah, so for interreciprocity, what do we have to do?
Find the adjoint.
Yeah, we need to find a network which we call the adjoint network. And in the adjoint network, if in the original network we had R, L and C in a particular branch, we don't change anything. You retain the same in the adjoint network. If the original network had a voltage controlled current source, what do? We just retain it but just flip it, right? If it is a VCVS, it's a CCCS and vice versa, right? Again, the sensing and the sourcing terminals are flipped, and also if it's a CCVS, it is a CCVS. And of course, if you do that, then the results we saw. Sorry.
In the last current, it was flipped direction.
Yeah. That you take care of the direction, right? So if we form this adjoint network, then the results we saw for the reciprocity will also be valid, and that is called interreciprocity. Okay. And one of the main applications of this reciprocity or interreciprocity is to help you find multiple transfer functions, which is what we want to find the output noise path spectral density in an RLC network, which also has control sources. Right? So let's say you have multiple resistors. So instead of finding the transfer function from each noise source to the output, you can directly apply a current and measure the current. Okay, great. So this is one easy way of finding the output path spectral density in a linear network containing RLC and control sources. But it turns out if the network only has RLC, there is we can do more simplification. So let's look at that today. So we'll consider only a linear network comprising of R, L and C. Okay, and actually I'll remove the resistors and take it out and show like this. And you have all this. Okay. And say this is the output voltage that you are interested in. And say this is the resistor RK. And this is the source denoting the noise generated by the resistor. So if I were to find the path spectral density at the output only due to this noise source, what will it be? This is the transfer function squared times the path spectral density, which is, for a resistor we know it is 4 kT times the resistor. This is only for one resistor. So for all the other resistors, we will simply add them. So it will just be summation. Right? Great. So But now we have a new weapon in our armory, which is reciprocity. We know that instead of finding this transfer function by applying a voltage here and measuring the voltage, we could as well, what can we do? So what do I do to the sources here? I null them, so basically it becomes a short, and I apply a current here, and I'm interested in finding the power spectral density at a frequency f. So I'll apply a sinusoid at that frequency f. So I'll just represent it using phasor, so it's 1 angle 0, right? Instead of writing cos, sin, whatever, I'll just say. So it means sinusoid has an amplitude 1, phase 0. So now if I look at the phasor current IK here, what will that be?
We are applying sinusoid here.
Yeah, I mean we are applying a sinusoidal current with a amplitude 1 and initial phase 0. It will be hk of f, right? I mean you know that if you apply a sinusoidal excitation to an LTA network, the response you have will be, I mean at least you know that the transfer function, if the transfer function from this source to the output is some hk, the transfer function from the current source here to the current here is also hk, right? So that's what we are doing, right? We are applying a current with an amplitude 1, phase 0. So you measure the amplitude and phase, that will just be hk.
It is for exponential signal.
Okay, for an LTA also it holds good, right?
Yeah, true.
I mean this question was, we saw if you apply e power j 2 pi ft, the output is h of f times e power j 2 pi ft. So what happens for cos? Let's say omega t. Huh? Yeah, I mean this is basically mod h of f times cos of omega t plus angle of that, right? And this is what we write as phasor, right? H of f. So, I mean you can work it out, right? I mean you know the response for e power j 2 pi ft is this. Cos is basically e power j 2 pi ft plus e power minus j 2 pi ft. So for e power minus j 2 pi ft, the response is h of minus f. This is same as h conjugate of f, right? For real systems, because this holds good. So use this result and you will be able to actually prove. Okay. So everyone satisfied that the phasor I measure here will be hk of f. That is, the magnitude of the current is scaled by magnitude of hk, and the additional phase will be the angle of this. Okay. Take it to the next page. Okay, so now that is fine. Then can you comment about the power dissipated in the resistor RK? I mean, IK is a complex quantity, remember. Why do you say real?
Sorry.
I mean, we have a current with an amplitude 1. Here, what is the magnitude of the current? Mod hk. So, you know, power is I square times R. So, here the magnitude of the current is times RK. Is that fine?
Would that be smart too, because
If you take RMS power, yeah, I mean, okay, fine. Let's say you take I mean, let's say the phases are all in RMS, right? I mean, that's it. That's your confusion, right? Let's assume that everything is in RMS, so you don't have to worry about scaling factor. So, is this fine? Great. So let me this. No change. So if I do summation k, RK times mod hk of f square, what does it give me? Is it what noise? No, no. I mean, RK times mod hk of f square, we saw is the power dissipated in the resistor RK. So this is basically the total power. I mean, there is no noise here, mind you. I mean, we are just considering, we applied a current source. Yeah, we applied a current source, which is sinusoidal current with an amplitude 1 phase 0. And then we saw the current is this. So current square times the resistor gives the power dissipated. So this gives the total power dissipated in all resistors. Is it fine? So now stare at these two and tell me what SV out of F is.
So total power dissipated in the resistance when we give 4 kV of the.
No. I mean, okay, this is a separate thing, right? This is the network we are interested in. Okay, we are supposed to find the output power spectral density, and that has an expression of this. What we did was we applied now a current. There is no noise here. We applied a current, phasor 1, and measured the currents, and we did this. This gives me the power. So this entire thing is basically the power dissipated in all the resistors if you apply a sinusoidal current with a phasor 1. Okay, is it clear? So now this portion is, this entire summation is basically this. Okay, so the output power spectral density here is 4 kP times the I'll say the power total when you apply a sinusoidal excitation basically. Series much interesting. Yeah, so this is the total power dissipated in all the resistors when you apply a sinusoidal current here with a phasor 1. Is that fine? In okay, so let me so now we know that this network here contains only R, L and C's, and here I have applied a current 1 angle 0. So I can basically simplify this and find the equivalent impedance, right? Is that fine? And I will say this sum Z out of F. Okay. So now I am applying a sinusoidal current with a phasor 1, and that is pumping current into this complex impedance. So what is the total power dissipated in the impedance? Sorry? Why did you say 0? No, Z out is a complex number, right? So this has both real and imaginary part. Only the real part will consume power, right? Because that's the real power that's dissipated. So this is basically now what is the power? Yeah, it's I square times R. The current magnitude is 1, so you are saved. So 1 square times the real part of. Is that fine? Great. So now we know that this network again contains only resistors, inductors and capacitors. If this power is dissipated in the Z out, which elements do you think will dissipate this power? Only resistors. So I see that the total power dissipated in the impedance is this, and the power dissipated in the resistors is basically this, right? So what can you say about these two? They are same, right? Everyone convinced? This is the total power that is dissipated in the impedance, and this impedance itself contains only resistors. So the power dissipated will be only across all the resistors, and that we have already computed to be this. Okay. So now you stare at these two and tell me what is SV out of F. 4 kT times real part of Z out of F, and because basically this is equal to this. Okay. So the bottom line is if you have an RLC network where all the elements are linear, we can find the output path spectral density by simply, this is the output. The output path spectral density is simply 4 kT times the real part of the output impedance here. Okay, and this result was shown by Nyquist. Yet another result from Nyquist. Okay, you can call this Nyquist noise. Right? Cool. So this is only with RLC. So what do you think? I mean, where in this entire derivation did we assume that we have only RLC? What happens if we have control sources? I mean, in the entire derivation, where did we assume that we have only R, L and C and we didn't have any control sources? Okay, let's retrace from the beginning, right? So we started with this. This can have control sources, fine. SV out of F is still this. Assuming only resistors are noisy, this relation is valid. Now, if then what we did was we used reciprocity. If I have control sources, what should I do? I mean, this will become adjoint, but this result is still valid. I can inject the current, measure the current, and that will give me HK. So the power dissipated in the kth resistor is still this, nothing. This is still the total power dissipated in all the resistors. So this result is still fine. Till here it's fine. So next what we did was we again this impedance can be reduced to, I mean, this should be the adjoint network, and we can again reduce it to an equivalent impedance. This is fine. Again a complex impedance. Power is dissipated only in the real part. So this is also fine. So what's the problem? Exactly right. I mean, till here everything is fine, but there is a crucial step we did at the end where we told that this power is equal to this power. That need not be the case if we have control sources, because depending on the configuration, they can also deliver power or dissipate power. Okay, so this result is fine and this result is fine. And to get the result for RLC, we use the fact that these two powers are equal, which need not be the case if we have control sources. Okay. So yeah, so that's about it. For RLC, you can use this directly, but if you have control sources, you don't have any other option. You take the adjoint network, use interreciprocity, find all the HKs by injecting a current, and you can find the path spectral density. So let's check it using a quick example. Say we'll take our here RC circuit. Okay. So here let's say this is the output. So the output path spectral density is 4 kT times the real part of the impedance here. So what is Z out of F? I mean, this is first order RC, right? Just 1R and 1C in parallel. What is that out of F? Why F? Huh? I mean, how will you find?
You are asking Z out.
Yeah, I mean, this is, they want to find the Z out looking here, right?
Right. Yeah, we apply current source. So it is.
Yeah, I mean, why do you want to do all this, right? It's just a resistor capacitor in parallel combination. So what is it?
It's R parallel, R into.
Okay, R parallel. Okay, let's do, right?
Yeah.
I mean, why? Yes, I'm looking at 1 by 2 pi FC, J 2 pi FC.
Yeah.
So what does it simplify to?
Can we write that result as 4 kT by real part of Y out?
4 kT by real part of I out.
Y out, like admittance.
Yeah, you can write. I mean, now you can think of it, right? And you have a complex number Z out. This is basically 1 by y out, but you see conjugate and all will be fine. So you take into account. But it's a LTI network, impedance and admittances are inverse of each other. That much is fine. From this we can write in terms of admittance also.
This is an LTI system, so Z out will be equal to 1.
Exactly. That is true, and from there you can rewrite.
But real part of setup does not.
Yeah, real part of Z out need not equal to real part of V out. That's the deal. It's a complex number, right? You take it. Yeah, so what is the real part of Z out then? I mean, this is Z out, what is real part of Z out?
R by 1 plus omega square.
I mean, just multiply the conjugate stuff, so it will be 1 plus square. So the path spectral density is 4 kT times this. Okay. And this is what you will get if you do the normal method also. So this is fine. So now we seem to have found some easier way to find the path spectral density for RLC networks at least. But say you want to find the mean square noise, which might be the case in many places. You might not be interested in how the noise spectral density varies with frequency, but you will be interested only in the total noise power in the output. So if you have the power spectral density, how will you find the noise power? Integrate it from 0 to infinity. And as we saw, this seems to be an awful waste of resources, because you seem to be accumulating a lot of information, but then discarding everything and looking only at the area of this, right? So let's see if there is a better way to do this. Yeah. So again, we'll look only at RLC networks. So this is RLC. Okay, I'll plot R again. Multiple resistors. This is RT. So you know SV out of F is 4 kT times summation K this is fine. This is basically 4 kT times RK, the path spectral density of each resistor noise, times the corresponding transfer function magnitude square, right? Cool. So now V out square is what? From here, what is V out square? I mean, to get V out square, what should I do? I'll have to integrate it from 0 to infinity. So I'll have 4 kT times summation K RK. Oh, sorry, there is no df here, right? Yeah. This times df. So what do you think we can do next? Yeah, that's the usual thing, huh? So I'll take 4 kT, I'll take summation K, integral 0 to infinity. Okay, let me actually pull RK also out. Okay, cool. Now, I know that we are dealing with real systems. So, what can you say about mod hk of f? For real systems, for real impulse response, it's even function. Magnitude is an even function. So, instead of writing the limit from 0 to infinity, I will say it's from minus infinity to infinity. It's 2 kT, fine. So now, can you look at this and tell me if some result or theorem you learnt? Huh? Parseval, right? What did Parseval say several years back?
In the time domain, if you
Yeah, this is equal to what? This is basically equal to mod hk of t square dt, right? And of course we know we are dealing with real systems, so hk of t is real, so I don't need to put the magnitude and all, right? So I'll just say hk square of t dt, right? And since we have causal systems, the limit need not be from minus infinity to infinity, it is 0 to infinity. Okay, so this is basically 2 kT summation k rk times this. Okay. Cool. Now we still haven't used our newly learned weapon. What is it? And we have been learning something for the last 2 classes. What was it? Reciprocity. So let's do it, right? And this hk of t, what is it? It is the impulse response from this, say, the noise source of the kth resistor to the output. We can get the same impulse response by, I'll take the same network. I will short this guy. I will apply an impulse current and measure what? Current flowing through this resistor. Okay, and say this is Ik of t. So what is Hk of t in terms of Ik of t? We saw in the beginning of the class, right? Yeah, I mean, this is, I apply an impulse, measure the response, but to be dimensionally fair, this has to be multiplied by 1 coulomb. Is that fine? So let me use these two to simplify things further. I'll take this also. So this is V out square is basically Ik square of t dt times 1 coulomb square. Okay. Cool. So let me make some changes to this. So this is 2 kt summation k Ik square of t times Rk dt fine. So what is Ik square times Rk? This is the power dissipated at a time instant t. Right? I am integrating this from 0 to infinity. That's the total energy dissipated in the in this resistor Rk. So what is this entire thing?
All resistor energy dissipated.
Sorry?
Energy consumed by all the resistors.
This is basically the energy consumed by all the resistors, right? So this is the total energy I'll say dissipated in all the resistors. And remember, this is the power dissipated or the energy dissipated when we apply this impulse current. That's also important. We should look at what is the excitation also, right? So when delta of t is applied. Okay. So let's say now I put an impulse current here at t equal to 0 plus, say the energy stored in the network is energy stored is some E0. I mean, put in an impulse current, basically pushing in a 1 coulomb of charge. So I'm injecting some energy into the network and calling it E0. As t tends to infinity, say the network has some energy remaining in the network, say it's infinity. Fine. So how are these two related to the total energy dissipated?
0 is equal to infinity plus dissipated.
Yeah. So this is basically 2 kt times. This entire thing is the total energy lost. That is basically what?
E0 minus E.
E0 minus E infinity. Again, just to be dimensionally consistent, it's 1 coulomb square. Okay, so this is 0 square. So now we seem to have gotten some expression for the mean square noise in terms of the two energies. So do you think this is easy to calculate, or I mean I could as well compute this integral? Which is easy, do you think?
Of course, the next one, otherwise why would you use square?
Sorry?
It should be easy.
Yeah, why this might be easy? Huh? Okay, that's a very logical answer, but technically, I mean, see, to find E0 and E infinity, what are the quantities I need in the network? I mean, how will you find the energy?
Energy stored around the inductors and capacitors.
Yeah, I mean, to find them, what are the quantities you have to compute? I need to compute voltages and currents at what time? T equal to 0 plus and t tends to infinity, right? So, whereas here, you have to calculate for all frequencies and integrate, but here it seems to be just two values, right? And luckily these two are, I mean, these two you can find it easily, right? Say, as t tends to infinity, in an RLC network you apply an impulse current. If you have to find the voltage as t tends to infinity, what will you do?
Open circuit capacitors and short circuit.
Right? And why is that?
We are finding the DC average value at that time.
I mean, actually, yeah, I mean, that's a fine point. We are not finding the average value, we are actually finding the total value. But being a passive RLC network, we know that if you apply an impulse, in steady state, voltages are going to be constant. Okay. So, it is as if we are looking at only the DC portion. And you know that since the voltages are going to be constant, capacitor current is d by dt, it is 0. So, you open all capacitors. Similarly, you short inductor. So, we can easily find it, and at t equal to 0 plus, the same thing, right? You short all capacitors. So, technically, this should be easy to find, right? So, let's quickly check it with the first example, which is this RC. So, here, this is the output. Okay. So, what do we have to do? Yeah, E0, but what should be the excitation? I should apply an impulse current at the output port. So, I apply an impulse. So, where do you think this impulse current will flow through at t equal to 0 plus? It will flow through the capacitors. So, what is V out of 0 plus? It's 1 by C. Again, this multiplied by 1 coulomb, only then you will get a volt. Okay. So, if that is the case, what is the energy stored at equal to 0 plus? Half times C times 1 by 2C. What can you comment about T infinity? I mean, in steady state, the capacitor is going to completely discharge. It has 0 voltage, so 0 energy stored in the network. 0. So, what is V out square? It's 2kT times E0, which is 1 by 2C, minus E infinity, which is famous kT by C. So, this might look simple. So, let's look at some more complicated network. Say, the resistor. And so we have, okay. So of course, now it is at least obvious that if you do the conventional way, it's almost impossible to do it, right? So now let's see, right? So what happens? I will have to apply an impulse current. Where will this impulse current flow?
This side of that. This all capacitors we have to short.
Basically, capacitors. Yeah, see, at t equal to 0 plus, only the capacitor is going to be taking in the current. So, you can redraw the circuit by doing this. Okay, only the capacitors will be there and the impulse current is flowing here. So, what is the effective capacitance you see? Yeah, this C3 in parallel with these two. So, what is first let's do V out of 0 plus. I mean, you have an impulse current.
1 by 2 C equivalent of this.
Yeah, this is basically 1 by the equivalent capacitance, which is C3 plus whatever, C1, C4 by. Right? So what is E0?
1 by 2 C.
1 by 2 times this guy, right? Good. So what happens at t as t tends to infinity? I mean, this capacitor seems to have a path to discharge to ground. This capacitor also discharges like this. This also discharges like this. So finally, all capacitors will discharge fully, and the infinity is 0. So what is V out square? Mean square of this output.
80 by this C.
80 by this.
KT by this effective C, right?
Yes.
Is that fine? Let me do another example. So I will say remove this resistor. So what is V out of 0 plus?
C1 and series. No, C4, C1 parallel with C3.
Same thing as before, right? I mean, no, nothing changes because at 0 plus, anyways, don't consider resistor. So E0 is going to be same as before. That was half into C3 in parallel with series of C1 and this guy. Okay. Now, what happens as t tends to infinity?
So C3 and C2 does not have path to discharge.
What about C1?
C1 also does not have.
I mean, you can see that now the capacitors don't have path to discharge. So, and I know that in steady state, this is going to attain some constant voltage in steady state. And in steady state,
Current is 0.
Current is 0.
Resistors can be treated as short.
yeah, exactly. So, this current source is also not active.
C2 will come in parallel with C1 and 1.
Exactly, right? So, this current is 0. So, which means this current is 0. So, basically, which means these two voltages are equal. Similarly, this current here is 0. So, which means C4 is no longer in the picture. So, what is the final voltage? V out of infinity. How do you find it? Yeah, why do you say that? Yeah, I mean, initially you injected what charge? 1 coulomb of charge. So that is basically still stored in this network, right? We haven't lost it fully, so it's V out of infinity times C1 plus C2 plus C3. So this gives this. So what is E infinity?
1 by 2.
Basically 1 by 2 of this, right? Okay. And of course, these two guys, you can find what V out square is. Okay. So
we have lost. We might have lost some charge.
no, the charges will just get redistributed among the capacitors. If there is a path for the charge to get lost, it will.
So only C, because no capacitor has discharge at all.
Right.
That is why we have equated it to 1. Otherwise, we
Yeah.
would not have done that.
I mean, if there is some path to ground, all the capacitors will take that path and discharge. Right. If there is at least one DC path to ground, you can always find a path from any capacitor to that, to ground through the resistor. Right.
So, for example, in this network, if there would have been any node which is connected to ground,
Which
then
was?
connected to ground,
Okay.
then the capacitor will get a path to discharge.
Oh, basically, if it's ground, that capacitor is not in the picture at all.
Yeah.
If you are saying that if you have a switch and connect it to ground, that is not we are considering. We are taking only linear networks. LTA networks. We haven't talked about time variance yet. Okay. We will come to that later.
Is that case not possible where only partial charge is lost? Right?
You think about it, right? It will not happen. Okay. So what we have found is, so this result we have derived for RLC. So what do you think, where do you think it fails for the case with control sources? So let's start here. This is fine. V out square is, mean square noise is integral of path vector density. This is basic. This is also fine. And here I just modified this. Here Parseval doesn't care about control sources. And again, next I use the fact that HK can be obtained by applying an impulse current. If you have control sources, you just have the adjoint network. So this is also fine. So HK can be obtained by this. So till here it is fine. And this is the total energy dissipated in all the resistors. But if you have control sources, that will also be delivering energy or dissipating energy, and this guy will not be equal to this. That is, E0 minus E infinity will not be equal to this. Till last step it is still fine. So what we saw was 2 kT times E0 minus E infinity. I will drop that 1 Coulomb square. So it turns out we can simplify it slightly further to get some a famous result. And yeah, this result was actually shown by Professor Shanti Pond in one of the papers recently. So I'll share the paper also later. This result that you can find this in terms of the energies, right? So now we have this, and to find the energies, we have to take the same RLC network. And what do you have to do? To find the energy, what is excitation? I need to apply an impulse here. Okay. And if I apply an impulse, where is the impulse current flowing? It is flowing to the capacitors, right? So this is the time and this is the impulse current. V out of 0 will basically instantaneously rise, right? Okay, because it's flowing to some capacitors. So E0 is half times the capacitance something, I'll call it some C hat, times V out this. Okay.
So we are taking equivalent capacitance.
Yeah, the capacitance into which this impulse current is flowing. Right?
Overall networks.
No, if you apply an impulse current, you know that this impulse current will flow into some capacitance. It need not be the effective capacitance, right? See, in this case, it didn't flow through here. And if I didn't have this path of C4, the only path it will take is through this. Is that clear? So it is some capacitance, I don't know what it is, say some C hat, times the initial voltage to which, initial voltage V out of 0 plus square. So I'll write it like this, C hat times V out of 0 plus times V out of 0 plus. So what is this quantity? It is basically the charge stored in the capacitors, which is 1 Coulomb, because that is the charge you are injecting. So this simplifies to V out of 0 plus by 2. Similarly, you can do the same thing, and what is E infinity? From this at least, what do you think will be a logical thing to say? I know E0 is V out of 0 plus by 2. E infinity is, same thing. In steady state, you know that either all the capacitors are discharged or there is some capacitance that is holding a charge. Let's say there is some C prime, V out of infinity, and you follow the same thing, right? And if there is some equivalent capacitance still present, that capacitance will still holding this 1 Coulomb of charge. Okay, is that fine? So this part is fine. E0 is V out of 0 plus by 2, E infinity is V out of infinity by 2. So what is V out square? KT times Okay, so let me draw the network again. So this is the RLC network, and we have applied an impulse current. So this in time domain it is an impulse. If I go to Laplace, what is the Laplace transform of this? 1. And let us say the looking in impedance, the driving point impedance is Z out of S. What can you say about V out of S? This is V out of S. I mean, it is the current, which is, Laplace transform of the current, which is 1 times the impedance, which is Z out of S. Okay. So, is there something that that relates the Laplace transform to these two values? We have those theorems specially made for this. So, what is V out of 0 plus in terms of the Laplace transform? Right? And this is minus infinity is S tends to 0. So some conditions have to be satisfied, which will assume it's satisfied here. So this is simply kt times limit S tends to infinity S times Z out of S minus limit S tends to 0 S times Z out of S. Okay. So just hold on a final simplification. Okay. So again, this network contains only R, L and C. So Z out of S will comprise, will be made up of the impedances presented by each of these elements. What is the impedance presented by R? For inductor it is SL, capacitor is 1 by AC. So if I need to so if I were to scale this impedance by a factor K, how can I scale the impedance? What should I do to the individual resistors, capacitors and inductors? Every impedance here must be scaled, right? That is clear, right? This is K times K times K. Then this gets scaled. So let's say instead of choosing the factor to be K, I choose it to be S. Okay. It's a perfectly valid thing. So this becomes S times this times S. Okay. So this is basically S times R, S square L and 1 by C. And if I were to find this quantity, this is basically S times Z out of S. As S tends to infinity, what do you think will be finally present in the network? These two are gone and only this is present. So you can find this basically limit S tends to infinity S times Z out of S. You can find it by opening all the resistors and inductors and finding what is the remaining capacitance present, right? So R and L are opened and you find what is the capacitance. So 1 by that capacitance is this, okay? And since we are making the other, resistors and inductors open, this is labeled as C infinity, okay? Similarly, if I make S to be 0, what happens? This goes 0, this goes 0. So it's as if you short the resistors and inductors. So the last term here, how can you find this? R and L are short, and you find what is the effective capacitance remaining, and this is C0. Okay. So this finally simplifies to KD times 1 by C infinity minus 1 by C0, where C infinity is the effective capacitance you have when you open all the resistors and inductors in the network, and C0 is the capacitance when you short all the resistors and inductors. And this result was proved by Bode, the same guy who makes you draw the plots on graph. It's called Bode's noise. Okay. So again, this is a very handy way to find the mean square noise. So again, let's take the examples we had. We'll start with RC. So what is C infinity, or let's say C infinity. To find C infinity, what we have to do? I make the resistors open. So this is gone. This is C. And what is C0? No, I will short the resistance. So I will have this. It is not 0, right? 0 impedance. The impedance is 0, which means capacitance is infinity, right? Because 1 by SC is the impedance of the capacitance. This is infinity. So this basically KT times 1 by C infinity minus 1 by C0, KT by C. So let's say you take the third order RC, C1, C2, C3. What is C infinity? I'll basically open everything. It's only C3. Okay, so this is C3. And what is C0? All the resistors are short. So you have a direct short circuit. Infinity. So what is the mean square noise if I look here? KT by C3. So let's say look at the mean square noise here instead. Okay. So now I'll have to look at the equivalent capacitance here. When I C infinity means I need to look at the effective capacitance at my output node. Then I open all resistors. What is that? C1. C0 is, so this is short and this also short. It's infinity again. So mean square noise is KT by C. Okay. So now let's just make it a little bit interesting. So you have a capacitor here, C4, and say this is my output. What is C infinity? I'll have to open these things. C3, these two in series, right? That's what we saw earlier also. C0 is, I have a short circuit path from the output to ground, so it's infinity. So again, it's done. And look at the final example also where I remove this so that there is no path to ground. C infinity is what? The same, right? What is C0? I'll have to short these. So I'll have only these three capacitors in parallel. Let's see. Okay. Right. So if you have an RLC network, we basically can find it using two ways. 2 KT times E0 minus E infinity, or like this. Okay. And of course, remember, I mean, looks like this might be easy to do for LTE networks, but this is actually a more general, as we'll see, because you can use the same result for an LTE network also.
By calculating that from going from E0 infinity to C0 say infinity, I mean you got that V of 0 is
Yes. Okay, before this.
Yeah, correct. E0 is equal to V of 0 plus by 2. That I understood. But E infinity is V of infinity by 2. So why? I mean, there can be an inductor loop where current can.
We are only looking at the voltage, right? Steady state, the inductor voltage, I mean, in steady state.
Steady state also, inductors can also store current.
Can store current, but we are only looking at the voltage energy. I mean, we are only looking at the mean square of the voltage. See, the same result actually you can do if you are looking at the noise in the current. So there you will have E0 and E infinity in terms of the inductors.
I am slightly confused. I mean, if we are only looking at energy, and when you are looking at energy at 0 time and at infinity time,
Right.
yeah, energy can redistribute itself in capacitor and inductors also. I mean, it is possible, right? The energy can be distributed partially in
No,
capacitors.
if finally you cannot have only L and C in the network, right? If that is the case, it will keep oscillating, isn't it?
True.
Right? So I mean that is not something we are looking at.
True. Okay, so
The only possible way is either you have only a capacitor, loop of capacitors,
or
loop of inductors, or if you also have an inductor, you will have some path to ground that will discharge.
yeah, but my question is that when you are calculating E infinity, let's suppose there is no capacitor,
Right.
loop, but there is an inductor loop, and there will be energy in inductors. So, I mean, if you are calculating energy, then that energy, why we are not?
Okay, wait. If you are looking at only inductors, right? That's a okay. So let's say this is simple network, right? I don't have capacitors. Okay. So what is the, if I look at the voltage here, this is similar to what you are saying, right? Finally, inductor is still having something.
I mean, I was in the last slides and the example in the last.
Yeah, I understand. So you want to have a case where you also have an inductor here or something, right?
I mean, some loop which may be possible to have current at infinite time.
Yeah. So it's something like this, or you want to have
In
an
this case,
inductor.
dissipate, power will dissipate. Yes, something like that.
Right.
Yes.
So I mean the thing to notice, if you have something like this,
Current and
if you're looking at the voltage across inductor, what kind of transfer function you will have from say any voltage to the output? No, basically, let's say you take this simple case, or let's say this also fine. So let's say from this noise source, this is, or you wanted something like this, no? Or, yeah. So from this noise source to the output, what is the kind of high pass? Okay. So basically, I mean, ideally, if you integrate it, the noise will be infinity here. But of course, in practice, that will not happen because you'll always have some parasitic capacity. Okay.
Usually it will become band pass.
Yeah, band pass because you'll have some parasitic capacitor. In that case, whenever you apply an impulse current, that will only flow there. Yeah, understand. See, okay, you are asking as t tends to infinity, if there is only loop of inductors, right? So, if you might not have a situation like that, is what I'm saying, because each node you will have something like this in practice. Else, it will go up to infinity.
True. That I am not telling you. I'm saying that from the theoretical point of view, the result that you calculated in the E infinity, you didn't consider power in the inductors, energy in the inductors, but that is what my doubt is. Why didn't we consider any energy in the inductors?
Okay, you think about it, I'll answer tomorrow. I mean, see, basically you are still putting in that 1 coulomb of charge that will still be present in both capacitors and inductors, right? You think about it, I'll answer. Okay. So yeah, the want you to remember is these two results. Okay. So for LTI, I mean, if it's only LTI network with RL and C, this might be easy to do quickly. But we'll see. This is a more general result that you can also apply for time varying networks.
Both these results are right for every.
No, only this one.
Only first one.
We'll see later. Yeah. Okay.